Hello, my name is David Parks. My project is predicting batting average with StatCast data. The motivation and background behind my project was to explore baseball from the perspective of ability-based statistics and explain why batting average is not necessarily a great indicator of how well a player performed, and I wanted to visualize why expected batting average is generally a fair measure. And I wanted to apply machine learning to a topic that I'm interested in and use statistical tests to measure that output. My research questions were how predictive of Major League Baseball players' batting average are the statistics strikeout percentage, average exit velocity, um, average launch angle, barrel percentage, hard hit rate, and sprint speed. Number two, how does the model's predicted batting average compare to StatCast's expected batting average? And number three, how does the accuracy of the prediction change when expected batting average is used as the label? My methodology included cleaning and filtering the data, training the model using the aforementioned statistics, running that trained model on data to produce a prediction, and then creating two new columns using that prediction as a measure of accuracy, and then calculate the mean squared error and p-value of that prediction, and then create plots visualizing them, and then doing somewhat similar analysis on two more sets of data. So my results for my first research question was generally the mean squared error was in the 28 to 36 range, and that was after multiplying the prediction and the batting average by 100 because they're decimal figures. The p-value was very, very small, and that shows that the predictions were statistically significant. Generally, the accuracy got much better as the sample of at-bats increased, as you can see from the slope of regression on the figure to the right. And when the model was ran on a data set that had a minimum of 400 at-bats, the mean squared error was much improved, ranging generally between 7 and 11. The results of question 2 were that the expected batting average is significantly more accurate, with an MSE of 12.184 and even smaller p-value, showing that it's even more statistically significant. It had very similar behavior as the sample of bats increased, as you can see from the graph on the right. And when the model was ran with a minimum of 400 bats, it had an even smaller mean squared error. The results of the third question were that the mean squared error when the model was ran with expected batting average as the label was that the MSE was quite lower. It was between 11 and 13 as compared to 28 and 36. And the p-value was even smaller, showing that it was even more statistically significant. Again, very similar behavior as before, but the slope of the line of regression was less steep, showing that it was less affected by the sample of at-bats. So some of the main takeaways were that expected batting average is generally more correlated with the skill-based statistics than batting average. The machine predicted expected batting average is closer in accuracy to the expected batting average than it is to the machine predicted average. The batting average is generally very volatile as a statistic, and especially at very low samples of at-bats. And the expected batting average is seemingly more emblematic of a player's talents and potentially more predictive of future results. The future work that I could do on this project would be spending more time playing around with the parameters and features or models, and trying to improve the accuracy, and then potentially do similar analysis on the other expected stats that StatCast has to offer, and then maybe playing around with the features depending on what that statistic might be. And then I wanted to maybe pull in historical data for players and then analyze trends that might exist and see what influences those variations the most. Thank you for your time.